Welcome back, everyone. Hope all are ready to gain more knowledge from the coming experts in our session. So, it is a reminder to all the participants that the link for the MCQ will be shared at the end of today's session to your registered email IDs, and it is mandatory for all the participants to submit their response by 6:30 p.m. today to obtain e-certificate for this FDP. So now I welcome our second speaker, Dr. Arindam Biswas. Dr. Biswas is an associate professor at the Department of Architecture and Planning, IIT Roorkee. He has a doctorate in urban planning from the University of Tokyo, a master of city planning from IIT Kharagpur, and a bachelor of architecture from Jadavpur University, Kolkata. He is the recipient of the Institute Research Fellowship at IIT Roorkee from Outstanding Young Faculty, the ASEM Duo India Fellowship and DAAD Fellowship Germany, and the MEXT Scholarship from Japan. He has also undertaken a certificate program on international environmental leadership, Asian Program for Incubation of Environmental Leadership from the University of Tokyo. He is presently pursuing research sponsored by different research foundations of the Government of India like DST, the Ministry of Education, ICSSR, the Ministry of Environment, Forest and Climate Change, and NBCC. He is also working on research sponsored by Royal Academy of Engineering, British Council, and GCRF, United Kingdom. He has also published four editorial books and contributed to nine book chapters. He has recently completed a book to be published by CRC Press. He has over 70 publications in peer-reviewed journals and international conferences on urban infrastructure, inclusive growth, resilience, housing, and informally knowledge, economy, and regional development. Dr. Biswas will be focusing on factor analysis and linear regression application for validation of hypotheses that are very essential part of any research that needs to be done in the field of architecture and planning. We welcome you, sir, from the part of a FOIP family. Please help us to gain more knowledge on this particular topic, that is linear regression.
Thank you for this introduction and generous introduction. Uh, Thank you all for joining this session and also uh, switching on for this lecture. I hope it would be as interactive as possible and also as explanatory as I can. But please pardon me if something I may not able to explain as I would like to. Uh, okay, thank you, and sorry for this trouble. I hope you all can see my screen. So I've been given this task of telling you a little bit about analysis techniques, and this is the very basic things that probably most of our social scientists spare, and including planning and architecture students, they utilize this very basic techniques to analyze some of the observed variables, right? I think till now you had a very detailed understanding about what research are, how you can do research, how you can probably uh, derive objectives, and how you can also have some sort of ideas about proving those objectives, right? So the major task, I believe most of you are either are working as your own way as a researcher, or maybe working as an academic researcher doing PhD, or you're working or you are doing research for your own satisfaction. So these are the very basic two techniques that you may consider when you get a huge set of data. right? The first thing, research is very kind of a systematic step-by-step methods where one step leads to the another one. So when we do researching, that means that we try to do something, we try to invent something which the knowledge is not available within the present domain of our literature. So we try to add something uh, in the literature which is being observed through our understanding or our process of collecting data. Now we can collect data either from already published document. Most of the time we take those documents in the form of, let's say, if we talk about urban planning or regional planning, in some cases in architecture, we get those kinds of data from census information, from different sample survey information, or different levels of census. Sometimes census is being done in the district level, sometimes census is being done at the block level, and we have the decadal census, which is being the comprehensive document that is being done at the national level. So if you can go to the next one. Yeah, next slide. Yeah, so this may be coming out of the blue because I have seen your proposed syllabus, and then there is not much statistical information or statistical tools or techniques that was there, but it was given as a kind of, and probably came out of your own understanding or your own requirement, that you need to understand what factor analysis and the regression that is more important for testing of or validating of our different hypotheses. Now, factor analysis is, from the name probably you could understand that we try to do certain kinds of reduction of large set of data, right? Most of the time we probably do not use this in everyday researches, but sometimes we end up either collecting or either procuring large data sets, which is significantly big, in order to uh, either do statistical analysis or to make certain kinds of observations, certain kinds of understanding from those analyses. So basically, it is to reduce data. So suppose you have an observed variables, that is, you have collected some questionnaire or from some secondary sources, a data with maybe 1,000, 5,000 or 3,000, something like that. So it is significantly large in number. And when we have this kind of data, especially in our kinds of field, it is also spatially segregated, right? We have, sometimes this data can be from the whole city, sometimes it can be a metropolitan area, sometimes it can be from the whole district. So we also have we have these data both in terms of space and also in terms of times, because we collect this data on very specific date. But in order to read or refer this data with another data where you may not have got those data in this much amount or this much in detail. So in order to compare between a data which is, let's say, 20, 50 or 200, and you have certainly a data set which is 3,000, 4,000, it creates a lot of imbalance, right? So we try to make every observed variables on the same scale in the sense that at least similar observed variables. Let's say if we try to minimize all those data within the least data that we have procured of one observed variable, maybe 50 or 20 or 25, whatever be the number. So that is the technique that we use, factor analysis, to shrink the data set. Okay, next slide, please. Okay, now the second thing is that when we are discussing about data reduction, and we are observing data in the two-dimensional state, right? So suppose if you can recall our XY axis, please pardon me, because it would have been very good if we have a face-to-face interaction. We could use the traditional board to explain it a little bit more in detail, but I am trying as much as I can to explain, make you explain visually, because at the end we are planners and architects, so we are more visual scientists rather than more based on literature. So what we do in factor analysis is that, or any kinds of analysis where we try to find relationship between 2, 3, 4 observed variables, where there is no non-linearity. Non-linearity means that there is no increment in the data set within itself, which create a function which does not obey the rule of linear matrix. So suppose if you remember the linear equation y equal to mx plus c, so that means that it doesn't have any kinds of incremental data which does not obey to this function of the linearity. So the factor analysis is something where we can only apply when there is a collinearity among the observed data set, right? So there should not be anything which replicate data of, let's say, a parabola or hyperbola or a nonlinear regression analysis, right? So in that case, we cannot use factor analysis, and we have to rely on some other statistical method to shrink or reduce the data set. Next slide, please. So just to give you an example, that this is, for example, let's say very simple equation I was referring to, and where we are observing between one dependent and one independent variable, and here we are trying to provide the same set of variables in terms of factor analysis equation. Now here you have seen that there is an object of error that has been included. Now the question is why we have included the error. And the understanding is that when we are shrinking large data into smaller data sets, when we are reducing those data sets, there are always, like, what happens when you shrink something, something gets lost within those data set itself. It's not really the replication of the exact amount or exact accuracy of data that you have collected with those 1,000, 5,000 observed variable into a smaller format, but in the process of reduction, some data are lost. So that lost data is being represented as the error. Right? So our basic aim or objective is to reduce the error as much as possible, so that we get an data which represent the larger data set that we have collected, and also reduce the error. So that means that our reduced data set represent as much as possible to the actual data set, and we can still use that for our analysis and get a result as accurate as possible, right? Next slide, please. So just to give you an example, that, for example, you have this, let's say, a linear equation which has multiple variables. So you want, our aim is to identify x, and we have some constant and also some variables in the equation, right? So li1, f1, li2, f2, and it will continue to the nth or kth function, and in the end we have the standard error of ei. So I is the error for, we have considered that there might be multiple error for multiple data reduction. So suppose we have 1,000 data, we are reducing to 50. Now from data number 1 to 50, we have got an error of E1. Data 51 to 90, we have got a data of error E2. So that is the summation of the error that is being given at EI, right? So as you can see that this xi is the observed variable, so that is the function that we want to achieve or we want to analyze, and that that is being analyzed through the collection of, let's say, 1,000 data set, and the error that we have identified in terms of EI, that is the error of the cumulative reduction that we have. In the process, you can also remember, because variance and covariance, this is another two terms probably you will come across even in your linear regression analysis. When you do multiple linear regression analysis where you have multiple variables, so the first thing as a researcher, you need to know that why you collect or why you consider these are the independent variables. Independent variables means which doesn't have any influence. You are collecting the data on that particular variables. Now, when you include this many numbers of variables in order to identify one dependent variables, so that means you have a hypothesis. You have a hypothesis through your literature review. You have an hypothesis through your experience, through your observation, through your understanding, that all these matrix, all these variables that you have identified and started collecting data will influence your dependent variable, right? So they have a relationship. So that relationship you already know qualitatively, that the relationship exists. Suppose you, to give you an example, that let's say you want to identify the relationship between inequality and income growth, housing ownership, job opportunity, and let's say education level. So you have these four independent variables, and your dependent variables is, let's say, inequality. So your hypothesis is that all these four variables attribute or contribute towards inequality in the society. So now your job is to prove that through regression, right? So you have all these multiple four variables, and you try to prove your hypothesis that it has a relationship with the inequality in the society. But it doesn't mean that there no other variables exist in the in the observables basket. There are also many variables which contribute to the inequality, but in your research, in your hypothesis, you have considered these four or these three, whatever. Okay? So the remaining which you could not consider because of your time, because of your limitation of one researcher, is all the limitations that you express in your research. So what we have to also observe, that what is the relationship between those observed variables, between those independent variables. That also we need to identify whether these independent variables factor each other or cancel each other in terms of their influences. Right? So suppose you have two independent variables of, let's say, economic situation or housing ownership, and also education levels. So we also need to know whether these two variables are mutually exclusive or not, or whether these two variables also influence each other or not. So that is the condition where we need to have need to understand about the variance and covariance matrix of our variables before we go into the regression or your factor analysis. Next slide, please. So to give you a brief idea that what are the objectives of factor analysis. So the objectives are, it compresses data set into a smaller data set, and the overall goal is to definitely, like, we want to reduce the factors and to explain the common themes amongst the given set of variables, determine the extent to which each variable in the data set is associated with a common theme or factor, to provide an interpretation of common factors in the data set, and to determine the degree to which each observed data point represent each theme or each factor of those analyses. So, next slide, please. This slide you can refer, or also you if you wish, you also can skip this one. This is to give you an idea to what are the different, or when to use factor analysis. But as I also already explained, that whenever you have a differential data set in your observed variables, or your independent variables, you can use this factor analysis for reduction of a particular set of data before you go into your linear regression or any kinds of other regression analysis. So factor analysis is not necessarily will give you or will provide you the hypothesis testing, but it will give you the platform where your data set are unequal, to make it more equal, and then you can carry on your actual analysis, right? Next slide, please. So if we can divide in terms of factor analysis, so there are, the most commonly used factor analysis is PCA, that is a principal component analysis, which is being extensively used by the social scientists in order to reduction of data sets. For example, we were having a research discussion yesterday, and a candidate has collected data on flooding, for example, from the census handbook, and there are multiple or a huge amount of data on housing condition at the block level in a district of Bihar, right? And then there are some data which the candidate has collected from the primary survey. Now you can imagine some data which is extensively from the secondary literature, huge amount of number, and primary data always has a limitation that you can how many data you can collect, maybe 250, 300, 400 sample surveys. So with 400, with 4,000, there is no match actually. So then what was identified, that if we can use PCA, or principal component analysis, in order to reduce the data and try to see the collinearity, try to see that what is the variance covariance, what is the error that we can reduce in terms of standard error reduction. If it is within our permissible limit, then why not use that data to make our data more homogeneous in terms of at least the sample size, where the revised data or reduced data do not lose the actual essence of the data that was given from the secondary analysis. There are some other methods as well. For example, image factoring. Probably those who work in the GIS mode very extensively, probably you use this in the GIS function itself, right? So you don't really do the statistical analysis in terms of, let's say, R or SPSS, but that function is inbuilt in the image processing mechanism, which try to factorize image factor reduction of data into a sizable data limit, keeping the essence of the large data set. And there are some other methods. Among the other methods, probably you will be more experiencing IGN values and IGN vectors. But rather than that, all other, probably you will not have much of the implication in our research fields. Next slide, please. So why we use factor analysis? So there are many advantages. I have put forward 5 of such advantages. First of all, the interpretability. Since we have a differential data set, it gives us a better or a possibility to infer our data within our limited knowledge or limited capacity to remember. Right? If you have 1,000 data, we cannot remember that much of data, but 20, 25 data set, yes, we can remember those kind of 50, we can remember. So that interpretability as human being or the limitations of human memory give us better chance without losing the accuracy or much of the accuracy of the data. It is also measurable attribute, both in terms of subjective and objective, and it is an established statistical technique. So there is nothing wrong in terms of research method or analysis framework of using this data, using these analysis techniques. There might be some implementations can guarantee uncorrelated features. So, for example, if you the results of factor analysis can be converted into another algorithm or in such features that cannot handle uncorrelated features. So correlation between or linearity between the variables, independent variables, can be avoided through using of the factor analysis. It's a flexible approach, so you can use more independently without much of the thought of its accuracy or much of the thought of its implication rightness or something. And it is not sensitive to the scale of variables. That is the most important thing. Like, it doesn't mean that how many of the data or how many rescaling that you do through the process of the reduction. It can be a huge amount of data that can be reduced in very small amount of data set. But the only thing is, as I mentioned in the first couple of slides, that our only intention is to reduce the error. So the error should not be significantly high in terms of data reduction. That's the only thing that we have to look into. Next slide, please. So some of the assumptions for factor analysis, because whatever we do, whatever we analyze, it's not exactly accurate, right? We are getting something which is an observed data set, which of course changes with time, changes with area, changes with when you change the your respondent. So everything changes, right? So that there is always should be an assumption. So the first assumption that you always reduce the data, right? So that means that your total sample size has to be more than the actual factor. And you cannot increase or stretch the data, but you can decrease the data. It is an interdependency method, so it should be no perfect multicollinearity between the variables. As I mentioned, the factor analysis is a linear function, so you cannot use or cannot reduce data which have non-collinearity or which provides different kinds of function than a linearity, maybe parabola, hyperbola, or something like that. Yeah, so it's also based on the linearity assumption. Next slide, please. There are some limitations. You can also mention in your research that these are the limitations, but that doesn't mean that you cannot use this technique. So first of all, sometimes you end up with incomprehensive results because you are reducing the data set, and then there are some information which invariably will be lost. Non-identification of complicated factors, because how it reduce the data set from, let's say, 1000 to 50 is by reducing the uh, by reducing or taking average of the data set which is close together. Let's suppose if in your 1 to 100 data, you have identified some data which is very close in their variance. So what they do is that they reduce those gap or take a mean of that and provide that into one data or two data, something like that. So that means there might be some data set which is not falling in the linear or not falling exactly or close to each other. So there will be some data which is very different from the existing collection or group of or set of data set. So sometimes it's very difficult to for those kinds of data to identify, because invariably those are the lost data which will be redundant or which will be not considered when factor analysis shrink this data set. Of course, it relies on theories, and probably some of you are also working these days with the advanced, let's say, AI or machine learning algorithms. So, factor analysis skills can be imitated by machine learning algorithms. So, it is not necessary that you do it through your paper. You can create or you can write models uh, uh, to implement factor analysis using machine learning algorithms, so that you don't have to do it manually. It does not handle missing data, as I was mentioning, because the data set which is little bit away from the average or the set average of the sets will invariably will be lost. So that way, that's how they reduce the volume of the data. Sometimes it cannot produce meaningful output if variables are not correlated. Right? So that means that the variation in your response, the variation in your data, if it is extensively high, then probably it is not a wise decision to do factor analysis. So then probably you have to divide those data set into multiple sets using set theory to do factorization rather than directly use that into factor analysis. Mm, Next slide, please. Someone is saying something. Okay. In statistical or spatial analysis, in statistical data, factor analysis is typically used to identify underlying factors. It can be explained the correlation among a set of variables. In spatial data analysis, it can be used underlying factors in terms of spatial variations among a set of variables. For example, I was mentioning that in GIS, if you are using extensively, it is inbuilt that how it reduced the data or how it avoid the redundancy of the data. It creates a matrix of variables and represent different spatial units such as census tracts, pixels, or polygons. And you can use the factor analysis to identify the common factors that explain the spatial variation among the variables. One of the common application of factor analysis in both statistical and spatial data analysis is in the data reduction and the data exploration to identify the underlying patterns or structures of the data. Next slide, please. So this is give you some brief idea how statistically, if you do it manually, how factor analysis involved, or how factor analysis function. So first, within the variables, they identify the correlation. So based on the correlation, different sets are being created. Then there is the number of factors to extract. So suppose from 1000 to 50 or 20, 25. Then those factors are extraction, which is these three methods can be considered as the principal component analysis of the principal components among the so many variables you have identified. Then there is a data mixing that happens through mostly through your analysis in a model establishment or rotation and derivation of the factor scales. So just to give you graphically, if you can see those rectangles on the top, so you have, let's say, a huge amount of data which is being observed through this rectangle, and you have identified that some of these data are correlated, the remaining data are not. And then from that correlation, you created the factor pattern through your correlation matrix. So that's how step by step in the process you create the data set. So similarly, in the Excel chart, you can see that there are some observed numbers which are very close to each other, right? So those observed numbers. So those observed numbers are very close depending on their variance and covariance, and that can be converted into one factors and reduced into reduction of the subsequent data set. The other numbers, you can see that they are not close enough each other to be grouped in one set itself, right? Okay. So next is next slide, please. So next we will discuss about the linear regression. Do you have any question, any observation, any like? Let it be very open, because you all are probably working as an architect, planners, or working as faculties. So if you have anything to contribute, please feel free to do so.
I think, sir, we can go forward.
Okay, okay. Thank you. So next, we will be going into the linear regression analysis. Next slide, please. So regression, so we can have one regression analysis with one dependent and one independent variable, or there can be regression analysis with multiple variables. So most of the time we do this multiple regression analysis where the data has collinearity, or data has a linear function. It follows linear function. It does not follow non-linear functions. So it's a statistical tool where we identify similarities. It's as simple as that. So in economics, in social science, many times in bioscience, bioengineering, in urban planning, in architecture, in most of the surveys that we do, which involves, let's say, household survey or opinion survey, we try to use this linear regression to see the data linearity and how it influences your dependent variables. Next slide, please. Okay, so this is the simplest form of linear regression. Y equal to mx plus c, or y equal to c plus bx, where you identify the dependency and independency. So C is the constant, and B is the regression coefficient, which gives you the slope basically, and X is the variable on which you are actually collecting different sets of data itself. Next slide, please. So what are the objectives of linear regression? With objectives are, first of all, to see their collinearity, whether they influence, and if at all, how much of their influence. So you probably have heard of the values, the positivity, the negativity. The more, the stronger the relationship, the value would be more close to 1. If it is positively correlated, then the value would be positive. If it is negatively correlated, the value would be negative. So those are the things that are major objective of linear regression. So we try to create and observe and predict value. We try to understand the relationship between variables, how strong it is, whether it is weak relationship, whether it is not so strong, not so weak relationship. So those kinds of observation that we find through linear regression. But there is another thing, especially for the researchers. It gives you the relationship, or the strength of the relationship, or the slope of the relationship, but it does not give you the reasons for those relationships, right? Sometimes what happens that once you achieve this kind of relationship, then you have to go one step further, extend your research process one step further, and try to identify why those relationship happens, right? Sometimes it requires little bit of observation, or it requires further analysis in detail, that why such relationship is happening, or what are the reasons that there are not so relationship between other variables, right? Because you can use the same model, take the data from other city or other village, and you may have identified or may have come up with a different set of relationship, right? So that also are very important for researchers, that to identify why such relationship, or what creates such relationships. So the causality, it allows you to explore those causality, but may not always give you the results directly. You have to probably work a little further to identify why, because once you establish the relationship, that means at least 60-70% of the work is done, that you have identified the relationship. That means your hypothesis, whether it is true or false, is identified. But the next step would be that why your hypothesis succeed, or why your hypothesis fail. Then estimation of coefficients, that is obviously you have to do in order to identify your slope, and the fitness of the model, whether your model is fitting with your hypothesis, or whether it is fitting with your testing of accuracy. So that is another aspect of your linear regression. Next slide, please. So when we use linear regression, I think most of you are well aware of. So just to recapitulate, that when we have the inference, or when we have as a primary goal, or inference is a primary goal, so that then at that time we use LR models, which give us the give estimate of the magnitude of the relationship between the outcome variables and your dependent variable or your independent variables. It can also be used as the baseline model, as I was mentioning. So in that case, it is a very prudent choice for you to use linear regression. It also gives you building the trust, right? That if you have a very strong correlation, if you identify, that means that it gives you confidence to openly support or openly say that what you have hypothesized or what you have understood through your observation or literature review is now statistically proven, right? So it gives you that much kind of an trust in your either in your predictive modeling or in your skill to build those hypotheses. Next slide, please. So mostly these six functions or six types of linear regression that we come up with. Most of the time we do number two, that is a multiple linear regression. Sometimes, very rare, we do polynomial regression where you use polynomial function, but most of the time you probably will be using the number two, which is variables of two or more in numbers of independent variables into our analysis. Next slide, please. Yeah, as I was mentioning that there are six types. So the fifth and sixth would be lasso and elastic net regression. Very rarely used. I have never used these kinds of regression. So probably you may require this, but this should be very, very special case for prediction. Next slide, please. So the advantages of LR is that it have interpretable coefficients. So they have easily interpretable coefficients that come along. And the confidence interval and the statistical test also signify those kinds of assumptions. Even in the recently extensively used machine learning in AI, you can also use LR. No hyperparameters, so they do not have hyperparameters that need to be tuned or need to be changed. It has a fast inference, so that means that it's a visualization technique, right? You have the data, but the skill for you to infer from the data is something as a researcher we develop. As much research as we do, as much experience as we gain from the observable variables, we try to or we can infer from the same data set. As I was mentioning, that it gives you the basic, but the inferences still needs to be inferred from your data set, and it is very well used and well understood by extensive academic community, right? So if you are using this in your research, I think most of the time it will be appreciated in the sense of it is very simple and it gives everyone and everybody understands this, right? So there will be no ambiguity, no confusion in terms of your analysis tools and techniques, or even in terms of you to make your audience understand. Sometimes in conferences or in your presentations, it is very difficult to make all audience understand what you're working on, because you are working, all the audiences may or may not be on the same research interest or do not have the same research interest, right? So at that time, such kinds of techniques allow you to make those kinds of discussions and also make your work understandable for the large academic community with scientific entity, because scientific authenticity. Next slide, please. So again, it is linear. So that is one basic assumption, and there is no multi-collinearity. The less, the merrier. So you have independent variables are not correlated with each other. So as much variant as they are, that would be helpful for your multiple regression analysis. If your independent variables influence each other too much, then probably it is not a good idea, or then you might have to change your variables itself. So that's why I was mentioning that your variance and covariance analysis will give you the idea of their mutual influence, and based on the results, you always can change your independent variables and introduce new independent variables in your ALR modeling. Okay, next slide, please. So the first assumption is that the ALR model, that the error are in the normal distribution. So if you put your errors in an XY axis, it is being distributed in terms of normal linear normal relation or normal distribution rather than any other kind of distribution. It also has homoscedasticity, so that means the same variance across all observations may cause due to many reasons, like presence of outliers or an incorrectly specified model. There is no autocorrelation, so it does not happen automatically. So there has to be independently identically distributed, and zero conditional mean, the error in terms of their conditional mean of 0. Next slide, please. So the other limitations, it cannot handle missing data. So if it cannot predict in terms of the data set, not peak predictive performances. If you use linear regression for prediction, for example, sometimes people use for population prediction, it may not be as accurate as some other techniques. You can also include machine learning models to make it more accurate in terms of prediction performance. In terms of linearity, in terms of relationship, it is the best one. But in terms of prediction, although you can use that, but it may not be as accurate as some other tools. Linear relationship between variables, it assumes that the variables are again related linearly rather than any nonlinear function, and need to specify interactions, right? Between should consider and you have to specify the interactions that the model should consider during the model building. Next slide, please. So as an architect or as planner, how we can use it in statistical or spatial analysis. So in statistical analysis, ALR used to identify and quantify the relationship between variables and to make predictions based on the relationship. So your prediction would be linear prediction, not non-linear predictions. In spatial analysis, ALR is used for model spatial relationship and to investigate how spatial factors influence the dependent variables. It can include pattern analysis and spatial autocorrelation, identifying spatial outlier and modeling the spatial distribution of a particular phenomenon. And ALR is a useful tool in both in terms of identification and measurement of relationship between variables, and which can be used in the prediction based on this relationship. Next slide, please. So this is one example of linear regression. So you have multiple data. You have a very simple linear regression, y equal to a plus bx, and then there are you provide summation of x, which is you add up all the x data set, summation of y, where you add up all the data set in terms of in y value, summation of x into y. So that means you multiply x and y and then make the summations. In if it is x squared, so then it means the data set you make it a square, and then you put that in terms of in the function and identify your y. So first of all, you have to identify the constant, and so a plus b, a and b value you have to identify using the x and y. And then once you identify a and b, so then we get the equation y equal to 1.5 plus 0.95x. So then you can put those value in a xy chart and get the relationship. So that's how we get the best fit model. So the observable data set in a xy are scattered. So for example, you have the first data, which is 2 from x-axis, 3 from y-axis. You have the second data, 4 digit from x-axis, 7 digit from y-axis. You have the third data, 6 digit from x-axis, 5 digit from y-axis, and all in positive. So there is no positive negative integration. And the last data is 8 digit on x-axis and 10 digit at y-axis. So all these 4 data sets are scattered. So what this equation give you? This equation gives you the best line that is optimum from each of these points, right? So that is our goal when we have regression analysis. So in this case, you have one dependent and one independent variables. You can do the same exercise with multiple variables and identify that best line which is optimum from each of those points where your data is being observed. So next slide, please. So if we can compare between the factor analysis, or if we can read together, if not a comparison, factor analysis and LR. The purpose of factor analysis is to identify or dimension, explain the correlation patterns among a set of observed variables and reduce that number of observed variables. And linear regression we use for the modeling purpose. We use to identify where that linear line fit among our collected data. Factor analysis involves a large number of variables. Linear regression generally small number of variables. It cannot have 1,000. It's very difficult, right? So in factor analysis, the variables are often continuous and typically assumed to be intercorrelated. And in LR, we considered either continuous or categorical or may not correlated at all. We have also assumptions for factor analysis, which is normally distributed the variables and that there is a linear relationship among them. In this case, it is also normally distributed and have constant variance across a range of predictor variables. Factor analysis involves correlation matrix among the variables. It involves analyzing the relationship between dependent and independent variables. So next slide, please. So how we can use FA and LR in combination to test hypothesis. Next slide, please. So it's a social and behavioral science observation, or where we can test all those hypotheses. So, for example, a researcher hypothesized that there is a relationship between a person's self-esteem and the level of social anxiety. So then factor analysis can be used to identify the underlying constructs that contribute to these measures, and linear regression can be used to test the relationship between them. So once you have identified the relationship between, let's say, or your hypothesis that there is a relationship between a person's self-esteem and their level of social anxiety, and then you collect a huge set of data, and then you can use like the huge set of data in different variables, then you can reduce those and create an underlying construct and then measure and then create model based on the linear regression, identifying the best fit line. Next slide, please. Another example, for example, you have hypothesized that there is a relationship between a person's level of physical activity and their risk of developing a particular health condition. So it's a relationship, whether it can be true or false. So with your data, you can identify that whether there is a bond, there is a relationship which is strong or medium or weak, or it is positive or negative. Right? So based on that, you can test whether your hypothesis or whether your hypothesis is true or false. So in the last, what we can say that factor analysis is used. Next slide, please. So factor analysis is used to identify underlying construct, while linear regression is used to model the relationship between the variables. So it creates the premise, and LR is used to do the modeling. And depending on the research question and data availability, one or both of these methods may be appropriate for your hypothesis validation. So that's all from me. If you can skip the next one and go to the reference sections. Yeah, so these are the references which you can use or you can refer to for your further reading and more for your more knowledge. So that's all from me. Thank you.
Thank you, sir. Now I open this session for all who have any questions or doubt. Please press the hand raise icon and you will be given an opportunity to ask the question from the sir.
I think there are no questions. Yeah, we have one question. Yes, Pooja.
Good
Pooja
afternoon, sir.
Yadav.
Yes, sir.
Yes. You're audible,
Uh,
but can you be a bit louder, please?
yes, sir. Sir, my question is, what is eigenvalue? Yesterday, I was reading a research paper and I stuck there. So I want to know about eigenvalue.
Okay. Uh, uh, I try to be as simple as possible. When you have a linear equation in a data set, and you have a matrix, for example, that you have 9 data which is being provided either positive or negative in the sense, and you have a data where both these sets or this matrix equation uh, has a relationship between in terms of its square root and also in terms of its square. So then the constant that is being associated with your collected data is measured as an eigenvalue and or in eigen value. So it is mostly being used in the algebra, and it's a kind of an vector which is associated with this kinds of equation. It's very difficult to explain without
Having that m by n matrix, it is very difficult to explain. Yeah.
yes. So that's I may not explain you appropriately, but yeah. So I'm sorry. So that's what we call eigenvalue, and its characteristic vector as an eigenvector.
Okay, sir. Okay. Thank you, sir.
Any other questions?
I think this
I,
was first. I would like to thank Professor Arindam Bishwas to accept my invitation and agree for the session. He is very busy these days. I know he is flying to different continents, to and fro, from Europe to India and so on. Where I do not know, rest he can say.
No, no,
But
I am here only. I
you're
was,
now in Roorkee.
yes, yes,
Okay,
yes.
thank you, sir. But still, he has agreed in one sentence. I said that you have to do it, and just in WhatsApp, and then he agreed, and I am really thankful for his acceptance. And in fact, I'm thankful for all the speakers who have accepted my invitation. They are all very busy these days and are holding different not only teaching, they are into varied type of projects, consultancy and so on. So thank you, Arindam
Thank
sir,
you.
for your kind presence here, and we had a wonderful session, very enriching, very uh, clear cut distinction between factor analysis and linear regression. I probably would like to say that I haven't seen such a very clarity in any of the books or whatever materials I have read together. It was my interpretation. But thank you so much for this detailed elaboration of yours. And I can see Professor BK Das also is here. Professor Das, can we see you once, please?
Just one addition, like in the probably in the slides that I shared, you also can share with all the participants.
Yes, yes,
There
yes.
is a book called Heinz, Montgomery, Goldsman, and Borrow, that is the probability and statistics in engineering. That is in the second reference slide, first book. I think now I don't see that book in Amazon, but earlier it was very available very widely. It is now out of print. But when we used to study in IIT Kharagpur, and that was the book which was the textbook, and I think it is one of the book which explains statistics very well articulated. Like even
Professor Somesh Kumar from computer science, mathematics. I don't
yeah,
remember.
no, we had Professor Ali who used to teach this
Uh,
from mathematics department.
we had Professor Somesh Kumar, and
So it would be like if you can collect that book, and it's very nominal price. I think 300 or 400 rupees.
mhm,
So it's this thick, but it's very good in terms of
very good
statistics and modeling. So
modeling.
that you can everyone can have that one copy. Yeah,
Thank
that's
you so much,
thank,
sir. Thank you for your time. Thank you for your presentation. Thank you for your knowledge sharing. I do not really know how to thank you once again, but formally I have to. And over to you, Arundhati.
and thank you, sir. Sir, it was really a lively, engaging, educative, and fulfilling lecture for all the researchers who are there in this FDP, and your insights, particularly on this factor analysis and variance and covariance matrix equation, and then you focused on all the assumptions that are there in regressions and in linear factors and all those things. So it will truly helpful for all the researchers who are there, and it will be lead all the researchers in their research that how to go of all the in detail analysis in their particular research. Thank you so much, sir.
I would just like to add one thing. We will be sharing you with all the slides and the slides of the presenters with their permission, and all the sessions have been recorded here, which will go live, which will be uploaded in our FOA AKTU website's YouTube channel. So we require a few days, and within Monday or Tuesday it will be done. So you can go through them again and again wherever your doubts are there, and you can contact us. So with this, I would like to end. I think we end this session today, and Professor Arindam, it's again a request to all the speakers, including you, if you could kindly make some more time for us in the valedictory session at 4 p.m., then we will be very grateful to all of the speakers and you as well. So we know you people, all of you are very busy, but now we'll break for lunch, and after post lunch we have another wonderful session by Professor Shubhranshu Goswami, and he will be accompanied by Professor Nandi, who both of them are going to give you the insights of patents, IPR registrations and patents. So that is the next part, and after that we have the valedictory session. Thank you so much.
Thank you.
Over to you, Arundhati.
So we have around 45 minutes of lunch break, and we'll meet again around 2 p.m. and we'll start with our third and the last session of this 5 days FDP. And it will be as told by Banerjee sir, that it will be a session will be taken by Subhranshu sir and Professor Nandi. So all are requested to join us back for this third and the last session of this 5-day FDP.
Thank you.
There's
Thank
a
you,
bit of confusion. I think our next session starts at 2:30, not 2.
Yes, sorry, sir.
Yeah.
Our next session will start from 2:30 p.m. and all are
2:30.
requested to be there.
So it's not 45 minutes break.
It's
It's more
almost,
than an hour.
it's more than an hour.
Yeah.
Yeah. Okay,
Thank
sir.
you.
Thank you,
And
sir.
see you all.
Thank you. Bye.
Thank you.